This is part 2 of my discussion about intermolecular forces, and what this will do is give some examples and relate intermolecular forces to boiling point and to solubility. Now, what we learnt from the last set of slides was that the intermolecular forces are related to the structure of the compounds. So van der Waals forces are usually for compounds that have just CH bonds, hydrocarbons. And then you've got dipole-dipole forces, which are for compounds that have a CX bond, where X is some kind of non-metal like nitrogen, oxygen, sulfur, or halogens. And then compounds that have an OH, NH, and FH are subject to hydrogen bonding. And what we also learnt was that as far as the strength of those forces go, hydrogen bonding is greater than dipole-dipole is greater than van der Waals. The relationship between these intermolecular forces and boiling point is illustrated as follows. Now, what we know about boiling point, first of all, is it's the temperature required to turn a liquid into a gas. Now, what we also know, and we talked about this in the last mini lecture, was that the liquid phase has the molecules touching and gas has the molecules not touching. So what we're looking at here is the energy required to have the molecules that are touching and as a liquid turn them into a gas where the molecules are no longer touching. And what actually keeps the molecules touching are these intermolecular forces that we've been discussing. And the key concept here is that the stronger the intermolecular force, the higher the boiling point is going to be. Now, going back to these examples here, what we're going to see is that we can look at the structures and figure out what the intermolecular force is going to be in each case. Now, for this one here, what we're going to see is this is all carbons and hydrogens, so that's going to be van der Waals. This one here has an OH bond on it. That means that's going to be hydrogen bonding. Whenever we look at a compound, we're only interested in the strongest intermolecular force at work. And since hydrogen bonding is so much stronger than any of the other intermolecular forces, it's going to overwhelm any other intermolecular force that also might be at play in any molecule. So we can see from the first one that we've got van der Waals on the first, hydrogen bond on the second. The question is which one has the higher boiling point? Well, since this one has the strongest intermolecular force, this one's going to have the higher boiling point. Now, in the last set, we talked about some of the other things that affected these intermolecular forces, and that was branching and chain length. Now, what we can see is we've got two things here that are both affected just by van der Waals, but the difference here is this is a straight chain and this is a branch chain. And what we already know is that if we've got a straight chain versus a branch chain, the branch chain is going to have lower intermolecular forces due to its shape. The straight chain is more cigar shaped, or like this, whereas this one is more spherically shaped when we talk about surface contact. So there's going to be less surface contact here. Less surface contact means lower intermolecular force. That means that one's going to have a lower boiling point. Alright, looking at the next one. We've got two different molecules here. This one's all carbons and hydrogens. This one has a CCl bond in it, so that one is going to be a dipole-dipole. Now, it's easy to look at this and think, hang on, isn't this going to have to do with branching as well? No, this has nothing to do with branching. Branching is only when we're talking about carbons coming off the main carbon chain. Here we don't have carbons coming off the main carbon chain, we've just got a chlorine coming off the main carbon chain. So we're not talking about branching here, we're talking about a completely different force, that being dipole-dipole. Since dipole-dipole forces are stronger than van der Waals forces, it's this one that has the higher boiling point. Looking at these two, the lower boiling point, we've got a dipole-dipole here, We've got a CX bond for a CBr here. We've got an OH here. That's going to be hydrogen bonding. Lower BP, we're looking for the lower intermolecular force. That's going to be this one. On this one here, we've got a case where we've got something where both contain some measure of branching, but this one has more branching. And therefore, the one that will have the higher boiling point will be the one with less branching, and that'll be that one. Now, there's also a relationship between intermolecular forces and solubility. We all know about solubility when we talk about like dissolves like. We talk about polar dissolving polar, non-polar dissolving non-polar. This could be taken back, though, also to intermolecular forces, because those are related to polarity as well. And what we know is that if we've got a hydrogen bonding solvent, something like water for example, which is all OHs, then the thing that's going to be most soluble in that will be something that has hydrogen bonding forces. If we've got a van der Waals solvent, something like a hydrocarbon, things that will have the highest solubility in those will be van der Waals type solvents. Alright, let's take a look at some examples of those. Now, when we're looking at these kinds of situations, we're interested in not just the intermolecular force of the compounds, we're also interested in the intermolecular force of the solvent as well. So we can know that this one is van der Waals. We know that this one is hydrogen bonding. But we also need to know what the intermolecular force of the solvent is. Greater solubility in this is the solvent. Since that's water, that's going to be hydrogen bonding as well. What we're looking for here is the one that has the greatest compatibility with hydrogen bonding, and that's going to be this one, which is also hydrogen bonding. So this one is going to be the most soluble in water. Looking at the next one, this one's van der Waals, this one's hydrogen bonding, this one is van der Waals. This is all carbons and hydrogen, so it's just van der Waals forces. Now it's asking lesser solubility in C6H14, so you're looking for the one that's least compatible with van der Waals, and again it's going to be this one, the hydrogen bonded one. Looking at the next one, van der Waals, dipole-dipole, van der Waals on the solvent. Lesser solubility in C6H14, it's going to be the dipole-dipole one. Van der Waals is more compatible with van der Waals. Next one, dipole-dipole, hydrogen bonding. This one, van der Waals. Now these are all different, so we need to discover a little bit about the compatibility of these. What we know here is that van der Waals is going to be least compatible with hydrogen bonding. It's going to be a little bit more compatible with dipole-dipole. So the one that's going to have the greatest solubility in van der Waals will be this one, the dipole-dipole. Looking at the next one, we've got van der Waals, we've got dipole-dipole, and we've got hydrogen bonding on the solvent. And the one that has the greatest solubility in hydrogen bonding will be the one that has the greatest compatibility with it, and that'll be the dipole-dipole. So that'll be this one.